In today's lesson, we are going to continue to look at kinematics, which are motion problems. So we're going to use integration in order to do this. So we're going to be looking at velocity time graphs, and we're going to be able to find position, we're going to be able to find total distance traveled, we're going to find displacement. So we're going to do all these different things now using integration. So in the first example, a car is traveling at a constant 50 kilometers per hour. How far does it travel in 2 hours? So to begin with, I just want you to logically think through this. You guys all know how to do this problem. 50 kilometers per hour, you go 2 hours, you know, your normal vector label. Hours cancel, so therefore you travel 100 kilometers. However, we could actually also do this calculus-based. If we did this calculus-based, what we would have is we have a velocity time graph. So this is our time, this is our velocity. So our velocity is constant. We're going at a constant 50 kilometers per hour. And then our time, we can travel for 1 hour, we can travel for 2 hours, we can travel for 3 hours, etc. So if we're traveling for 2 hours, what we are doing is we are finding the area inside here. What's the area? 2 times 5. 2 times 50. 2 times 50 is 100. So that's how you can do it with integration. Area under a curve within those set parameters. So we'll be doing this when they're not quite such nice graphs, but this is kind of what you're working on as well. Like, this is how it all connects together. Here's the thing. You didn't know, so the question is, do you know where the car was at the beginning? No, you have no idea where you started. Were you 5 kilometers from home? Were you, 17 hours into the drive? You don't know any of those different pieces. So all this does is tells us how far we traveled. So no, we don't really know where the car was at the beginning. So because of that, we can look at our position, which is S of t, based on time. So if we started at home, we'd be at 0. And then our position would go something like this. So if this is at 2, this is at 100. However, since we don't know where we started, maybe we started here, and then we went up. Something along the lines of that. So therefore, our position, S of t, is the integral of v of t with respect to t, which means it is the integral of 50 dt, which is 50t plus c. So this equation here is the 50t. This equation here is the 50t plus c. So again, knowing that we're shifting up, and then that we can find our displacement as well as our time, as well as our integration. Okay, so here's a velocity time graph. Because this is a velocity time graph, it tells me my total distance traveled being the area under it. Again, that integration piece, because I'm going backwards and I'm finding S of t. So I'm able to find my total distance traveled by finding the area underneath this velocity time graph. If this was a regular graph, I could integrate it. Like, so if this was a regular function, say it was some kind of cubic or something along the lines of that, I could actually integrate it and find it. Because this is a piecewise function, I have to find each individual piece. So the easiest way to do this is legitimately geometry. Find the area of each individual shape and add them together. Okay? So therefore, my distance equals this triangle, 1/2 base, which is 0.1, times height, which is 50. Plus area of a rectangle, so the horizontal distance is 0.2, times the height of 50. Plus, we'll do this little triangle up here. 1/2 my base, which is 0.1, times my height is 20. And then this rectangle is 0.2 times 30. And this triangle is 1/2, my base is 0.1, and my height is 30. So therefore, this is 2.5 plus 10 plus 1 plus 6 plus 1.5, which gives me a total distance traveled of 21 kilometers. Again, that was just based on finding the area of each of the shapes underneath. So, long story short, if you want to find s of t, you have to integrate v of t with respect to t. If you want displacement, displacement is different. Displacement is where you ended minus where you started. So even if I go backwards and forwards along the way, I still am just going to be able to find my displacement, where I started to where I end. So when we integrate from that start to the end of my function, I end up getting the displacement. If I want total distance traveled, so in this one we didn't have any overlap, so I could just add them all up and it gave me my total distance traveled. But if we would have went backwards along the way, then that wouldn't have given me my total distance traveled. To find the total distance traveled, you need to go through, figure out a sign diagram. So you know, where does it change? Where do you all of a sudden start to go backwards? Where is it negative? Or where does it go positive from negative? So you're going to have to do a sign diagram for v of t. So for your original function v of t, you'll need to do a sign diagram to see where does that negativity change. Then you will figure out s of t through integration. So you're going to then integrate v of t. Don't forget to include the constant of integration. And within there, you're going to be using s of a and s of b. Those are the starting points. And then you're going to find s of t. S of t being wherever that sign diagram changed its negativity, because we'll have to do each of those individual pieces separate. We are also going to draw a motion diagram. You don't have to draw a motion diagram to be able to do this. Like, you have to do this work. You have to figure out where does the sign changes. You'll have to integrate it. You'll have to find s of start, end, and all of the sign changes along the way. The motion diagram just kind of helps us visualize what's happening with it, and then we're going to in the end find the total distance traveled. And that motion diagram will help with that. Otherwise, you can logically sometimes think your way through it. But motion diagram is a surefire way to do it. Okay, so we have some particle moving in a straight line with the following velocity. How far does p travel in the first 4 seconds? So from the initial spot, 0 to 4. And then find the displacement of p after 4 seconds. Displacement, super quick and easy. How far it travels, not so much. So let's start with A, and then B will be a piece of cake. So for A, as we said on the previous page, we need to figure out a sign diagram so that we can figure out where does it change its direction. Where does it go forwards or backwards, etc. So in order to do a sign diagram, we set v of t equal to 0 because we want to figure out where does that change negativity, because that means it's going in the positive direction to negative direction. So therefore, we're going to factor that. So therefore, t equals 2 and 1. So my sign diagram is going to start at 0. And we're only going to get up to 4, but no big deal. It's only going to change at 1 and at 2. So therefore, I plug a value in like 0.5. If I plug a value in like 0.5, I put it into the factor form, which is typically the easiest. This is negative, and this is negative, which means it's a positive. A negative times a negative is positive. Put a value between 1 and 2 in, like 1.5. This is negative. This is positive, so that's going to be a negative. If I put a value bigger than 2, like 3, positive, positive. So therefore, I have my sign diagram. Okay, so that's the first step. I have to figure out where my zeros are. So the second thing we're going to do then is we are going to integrate. So we are going to integrate. So we are going to find s of t, which is the integration of v of t. So t squared minus 3t plus 2 dt. So therefore, when I integrate this, s of t equals t cubed over 3 minus 3t squared over 2 plus 2t plus c. And again, that c is because we don't know exactly where we started. So that's giving us our c value. Okay, so then we've integrated it. Now we have to find s of a, s of b, and then all of those values where it changed direction. So we need to find the start, we need to find the end, and then all of the ones from the sign diagram. So therefore, we will start with s of 0. So s of 0, if I put in a 0, I get c. Okay, that's the easy one. And then we'll do our first sign change, s of 1. So if I put 1 in, I get 1/3 minus 3 halves plus 2 plus c. Therefore, s of 1 is 5/6 plus c. And then I'm going to put my next sign change in, s of 2. S of 2 is 8/3 minus 3 times 4 over 2 plus 4 plus c, which means s of 2 is 2/3 plus c. And then my end, and if I had more sign changes, I'd have to do all of them. S of 4, when I substitute 4 in, I get 64 over 3 minus 3 times 16 over 2 plus 8 plus c, which simplifies to 5 1/3 plus c. Okay. From here, the motion diagram is helpful to see negativity. We're going to be using s of 0, s of 1, s of 2, and s of 4. So therefore, we start somewhere. It's c. So that's why I did s of 0. So s of 0 is c. That's wherever we started. We don't know what that is. Then we are going to take, so at s of 1, it's 5/6 plus c. That's positive. So from c, we're going to go to the right, 5/6 plus c. But at this point, there's a sign diagram, or sign change. So therefore, this is going to go opposite. So now from here, we are going to go the opposite direction at some point. And that takes me back to 2/3 plus c. So that's that horizontal distance. That's that x value, y value. So then we're going to turn back around because we had another sign change out here. And it ends right here at 5 1/3 plus c. So we started, there was a sign change at 5/6 plus c. So we turned around. There was another sign change at 2/3 plus c. So we turned back around. And then we ended, because it just said for the first 4 seconds, it ended at 5 1/3 plus c. So to find my total distance traveled, what I need to do is I need to find this horizontal, and this horizontal. And I'm going to add all those up. So think about how you find the distance between two things. Like if this was at 8 and this was at 10, what's the horizontal distance? 2, right? How do you find 2? You subtract them. So therefore, to find my total distance traveled, we are going to have to subtract them. So my distance is going to be 5/6 plus c minus c. So that's this part here. Plus, now I need this horizontal distance here. Now, because I know it's going negative, I need these to be positive. That's what I'm trying to find, is I'm trying to find my positive piece. If I just wanted displacement, I would ignore the negativity and I just add them all up. So I need to start with my bigger value, which is 5/6 plus c, and then I have to subtract 2/3 plus c. That gives me this distance. And then my last one up here, so again, I start with my bigger number, which is this one, 5 1/3 plus c, and then we're going to subtract again at 2/3 plus c. And then I simplify. All my c's go away. Every single c value goes away. You'll notice right here, c minus c, c minus c, c minus c. So all the c's go away. So then I just add up all my numbers, and I traveled a total distance of 5 2/3 meters. So that's my total distance traveled. So taking into consideration the backwards forward movement. Again, that differs from displacement. So for my displacement, all I want is my displacement after 4 seconds. So if I want my displacement after 4 seconds, I need to literally find where I was at 4 and where I was initially and subtract. So therefore, and that's in my s of t equation. That's my s's. These are my positions. So I had to go back and use either integration or I found these already. I found S of 0 after I'd integrated. I found S of 4. So therefore, when I put that in there, I'm just going to go back up here. So S of 4 is 5 and 1/3 plus C minus S of 0, which is C, which means my displacement, the distance between my start and end, is 5 and 1/3 units. I don't think I have a label, so units. Versus my total distance traveled is 5 and 2/3. Oh, maybe it's in meters. Yep, it's in meters. So therefore, my total distance traveled was an extra third of a meter. Not a big difference, but it is a difference. We can also look at acceleration and integrating acceleration, which will give me velocity. Same type of situation. In terms of story problems, you're just going to have to integrate A of t to get back to V of t. Okay, we've looked at this before. We know that the derivative of V of t is A of t, therefore the integral of A of t is V of t. So being able to go backwards and forwards with that. But this is the big focus on what we're going to be looking at. Not only this, but also total displacement. I lost all my pieces. There we go. So this is a big piece that you're going to focus on in your homework.